Hello everyone, my name is Gibert Bonet, and today I'll be presenting to you the paper Unsupervised Machine Translation in Real-World Scenarios. It has been written by my colleagues and I within the framework of the MT4All European project, and as you can see it takes into account several different institutions. Now, what have we done? Well, we have worked on unsupervised techniques for machine translation, because parallel data is not always available, especially for low-resource languages. There exist few open-source systems for low-resource scenarios, such as Opus MD, which use supervised techniques. Supervised techniques rely on having a lot of parallel data available, and we have just seen that this is not always the case, so they work with limited data. Another line of research is unsupervised machine translation, which relies only on monolingual corpora and has achieved impressive results in recent years. Now, unsupervised methods use standard benchmarks for comparisons, which means that they use high-resource language pairs such as English and German, and they are not actually low-resource. So in this work, we have expanded the use of unsupervised techniques to further domains and languages. Which are those languages and domains? Well, we work with 6 different domains: biomedical, customer support, financial, general, legal, and newswire, and 12 different languages. All the languages always go with English, and we have Spanish, German, Norwegian, Finnish, Latvian, Catalan, Georgian, Kazakh, Ukrainian, and Basque. Now, as you can see, we also include some high-resource languages, but since we have a restricted domain, we convert this case into a low-resource scenarios. Furthermore, all of our contributions have been already published, and you can access them in ALRC share from this QR code. And we have released 18 monolingual corpora, language-specific and domain-specific, as well as bilingual dictionaries, word embeddings, and the translation models that we have created. Now, the methods and resources that we have collected and developed within our project. First, the corpora collected. As you can see, we have very different sizes of corpora and also different sources. We have collected corpus from Escart, which is an openly available big corpus from the web, and usually it is considered general domain. We have also collected corpora by developing our own crawlings, where it says MT4All. This is data that we have created brand new. And then we have also used corpus from other available publicly datasets. Now, as you can see, the most amount of tokens that the corpus have is 2,200 million from the English General Escart, Spanish as well, and German as well, so high resource languages, and we can go up to the other extreme where we have legal Kazakh, for which we only have 1.8 million tokens. Now, you can see here the varying sizes and domains, and once we have collected all of these corpora, what we have done is we have built 12 translation models using Monoses from Arteche et al. And we have followed these steps. First, we create monolingual word embeddings. Then we map them and we obtain bilingual word embeddings. And from this, we can infer a statistical MT system that is finally used to create the neural machine translation system. Since we included some languages that are very rich morphologically speaking, we use VPE segmentation for Basque, EU, and FI, Finnish. And so the monolingual word embeddings at the beginning are actually subword embeddings. Now, how we have created these word embeddings, these bilingual word embeddings? Well, we use BECMAP as well from Arteche. And what this tool does is first it normalizes the length of the embeddings. Then it creates a dictionary based on similarity matrices. Finally, a self-learning step iterates over itself to improve this dictionary, and in the end the refinement step improves the dictionary based on symmetrically reweighting. We have also built bilingual dictionaries for specific domains. We have used TermSuit. You can access it here on GitHub. And the way we have done it is by extracting first English terminology, then looking at the statistical machine translation lookup table to obtain the corresponding terms in each of the other languages. And finally, we have applied a filtering step with a threshold to make sure that we only obtain high quality results. Talking about results, let's see the results of our project. We have used two types of evaluation, automatic and human, and we'll get started on the automatic evaluation, where we report S-Bleu scores for our model MT for all, our model with BPE segmentation MT for all plus BPE, and finally Google Translate. We include Google Translate as a baseline, but it is important to note that first, Google Translate uses supervised techniques, and also that the goal of our project is not to beat other systems, it's just to explore the expansion of unsupervised technique to other languages and domains. Well, we can see that the unsupervised models do not achieve parity with the supervised model, but this is something that could be expected, and that there is a lot of variability within the scores. For the English Basque general domain, we get a 5 of bleu, which is very low, but for the Spanish English biomedical domain, we get a S+ score of 40, which is a very considerable score for an unsupervised technique. So we have seen that there are some factors to take into account when analyzing the results, and that is the size of in-domain corpora, the size of general corpora that we have collected, the distance of the language from English, and also the level of complexity. So it is no surprise that the ones that obtain the lowest scores are Basque, Kazakh, and Finnish. Basque and Finnish are rich morphologically language, and then Kazakh is a very, very low resource language. So this could also be expected, and it actually has a different alphabet. Now, regarding Basque and Finnish, we can see how the BP segmentation boosts the results, especially for Finnish to English, and it is not so much the case in Basque to English. Now, let's dig into the human evaluation. We have reported human evaluation results for 3 domains: customer support, financial, and biomedical. For the customer support, all of the outputs were analyzed from English to other languages, and there were some issues very concerning that needed to be described. So first we saw that some named entities were translated. This is something that neural models are supposed to do, are known to do, right? So for example, Dear Barney was translated to Dear Rosendo, which if it's a user who's receiving an email, for example, this can really hinder the impression of the client towards this email. Also, there were problems with localization dates that were not performed. Mixed registers were found between formal and informal, some duplications, and some wrong parsing of URLs. So the conclusion was that these models were not ready for production and that they had some serious issues that needed to be tackled. Then, for the financial and biomedical domain, we have used the multidimensional quality metrics framework. For those who don't know, it is a framework that provides some categories that you can use for your error analysis, and you can choose which ones you want to keep to then perform this analysis. Now, in the case of the financial domain, we have only performed an analysis of 100 sentences from English to Latvian, and we found mistranslations, named entities that were also translated, some omissions and some typos, and the final MQM score is of 350. Now, the reference MQM score for humans to be able to say that a document has passed the analysis is 50. So you can see that 350 is a much higher number, and that's why we considered also that the quality of these translations were not very high. Because of that, we decided to explore 100 random entries of the English-Latvian dictionary that we have built using TermSuite, and we saw that only 70% were correct, and there were some other cases, such as 11% of them were unrelated, 10% were from the same domain but were different words, 4% were similar words, there were a few which were wrongly aligned, and finally there was a small amount which was actually the opposite words. So we think that This may also be the fact why we found so many errors within the English-Latvian domain. Now, finally, for the biomedical case, where we saw that the blue scores already gave us very good results, we decided to perform as well some human evaluation following MQM. We took the language direction English to Spanish, and we analyzed a complete full test set. We found some mistranslations, repetitions, and named entities, especially because it is domain specific. But the good news is that there were no fluency errors. The output sounded very natural, as it is to be expected from neural models, and the MQM score obtained was 138, which is much closer to what would be a pass for humans. So the results confirmed, the human evaluation results confirmed what the automatic results were already hinting at. So now, just to conclude, we can say that in low resource scenarios, completely unsupervised systems tend to yield poor results, except when the amount of in-domain monolingual data is big enough to compensate, as in the case of Spanish biomedical. We have also seen how human evaluation is necessary, and it is even better than automatic metrics to capture the output of an empty system, so we encourage the human evaluation in similar works. Finally, we are aware that in real-world scenarios there is always some access to parallel data, or that it can be created synthetically by triangulation or other methods. So, thank you very much. Here you have the references that we have used in this poster, but if you want to know more, I really encourage you to read our paper. Thank you. Have a nice day.